Welcome to Video Wissen. Cristina Chiappini, an astrophysicist from the AIP in Potsdam, did a presentation on her field of expertise, our Milky Way. This was done in the talk series of the Babelsberger Sternnächte. The title of the talk is Our Galaxy Has a History, Galactic Archaeology. Have fun!
So it's a pleasure to be here in Babelsberg at the Leibniz Institute for Astrophysics to talk to you today about where we live, the Milky Way. But our Milky Way in a larger context, and what are we, or me, or with a group working on, and is a field that we call Galactic Archaeology, which is, as you see, using the properties of the stars to try to infer the history of our galaxy. Because as you see, the galaxies are not something fixed. They are objects that have a history and have a lot of events during their lives, just like our lives. Here I start with this beautiful picture that you can just see by going to a place where it's dark enough. So that's why we have to be sure we have dark enough still places. And then look to the beautiful Milky Way that you see in this picture. So essentially, that picture is what you see in the sky, depending on the position you are in our planet. But this is the same picture then that Gaia, which is a very important European mission, sees, and this is exactly the same, numbers of stars in the sky. The difference that Gaia is in an orbit, and so can see the full Milky Way, and not only the piece that you see from either the northern or southern hemisphere. So this is not an image, this is just a number count of stars, so it's the luminosity of each star that Gaia measures, and this is being revolutionary to several fields, but of course for the field of mapping the Milky Way, and finally doing what we will see and understand that we do, which is called galactic archaeology. So the idea here is so that you understand what exactly is this galactic archaeology and how are we trying to map the Milky Way. Now, we cannot go out of our galaxy, so we cannot look our galaxy from outside. And so what you're seeing here is a cartoon, which was made recently by ESA Gaia as well. And this cartoon shows a spiral galaxy, which is supposed to be our galaxy, if you would look our galaxy from above. And you see the spiral arms, and you see something in the center, which is what we call bulge and a bar. You see something that has a form of a bar. This is the yellow dot I put there, shows where our sun is. And if you put other labels, you would see that these spiral arms have different names: the Perseus arms, the outer arm, the Centaurus arm, the Carina Sagittarius arm. And in the inner part, you have the bar. And the distance between the center of our galaxy, where we also have a black hole, and our position in the galaxy, the sun, is around these 26,000 light years, which we use more the word parsecs, which is the 26,000 light years are essentially around 8,000 parsecs. And we say often 8 kiloparsecs. That's where we are located in our galaxy, and we are in the disk of our galaxy. So, of course, this is a cartoon, because to make this kind of map, being inside the galaxy and inside this disk is very complicated. So, for that I would need precise distance, and then I could make a map of our galaxy, and we wouldn't need to use a cartoon anymore, right? Now, this is our galaxy. That was our galaxy from above, but I said our galaxy is like a pancake, and so it's very thin. And this is when I look to the galaxy from the side, edge on. And you see this is also cartoon, because we cannot see this from outside. And this, we see here what I told you before, the bulge and the bar, the disk where we are inside. And you also see that this disk is warping. So it's not like a flat disk. There are warp happening in the outer parts of the disk. This is again a cartoon. Well, the warp actually beautifully was recently mapped by one kind of stars we have in the Milky Way, which is called the Cepheids. The Cepheids are very bright objects for which you have a very nice relation between their luminosity and their period. They're variable. They have a variation in their luminosity that follows a certain period. And if you use that, you could then get a very good distance. And so when you use Cepheids are usually very young objects, and they are on the disk. And so because you have good distance for them, you can trace them up to larger distance. And you're seeing here, this is not a cartoon now, it's really one way to map the very young disk. And you see that you're seeing the warp in the Cepheids distribution. Now, what I would like to show you is that our galaxy has a history, as I said, and the things are changing inside the galaxy for different reasons. One of the reasons are the so-called secular processes that happen. For example, this bar can influence how the stars are changing positions in the galaxy. Here is not a cartoon, but is a simulation. What is a simulation? Is, in this case, any-body simulations, is the numerical solution that we obtain for equations of motion of a large number of particles, using gravitational force as the main force. So, in this simplified work, which I took from another group, you see here a galaxy like our own, as I show you, a disk, and you are seeing the edge-on and the face-on images. And now I will run in this simulation how in this simulation this is evolving. So, doesn't have to be our galaxy. You are seeing the evolution in time. Here up you have in time. You have the time in giga years, which is a billion years. And you know our universe is 13.7 billion years. So here we are seeing the first, 2 billion years. But this is not a model of the beginning of the universe. This is an isolated exercise of a galaxy that is a spiral similar to ours in some sense, to show that during this time that is evolving this movie, you see the disk, the bar and the bulge was a bit puffed out, which we call this buckling, and this has, if you look from above, you see now a bar that is pretty much similar to the cartoon I showed you before that we think our galaxy is. So this is one idea that we have, that things have developed in time. Another way is that another level of complexity that was only particles with gravity, but if you have also gas in these simulations, here I'm showing you another example from another group. Here in blue you have the stars, and in red you see the gas, and you see how this gas is evolving during this simulation, and slowly this bar is being created also in the stellar. The stars are also building this bar. What is the bar? These are stars that are in orbits that kind of design a bar. And the disk, what's the disk? Stars that are in orbits around the center of the galaxy. And they don't go up and low too much, so they stay in the disk. And you also have, of course, the halo stars that go plunging into the disk, but are not into the disk. So, and we have also the thin disk and the thick disk. So we have a very thin stars that are in these orbits very close to the mid-plane of the galaxy, and stars that do a little bit excursions from this mid-plane, but still define a disk, and that's why we call it thick disk. So here you're seeing now that the gas is giving you a very detailed, complex, I would say, view of the inner parts of the galaxy. The inner parts of the galaxy are the most complex part of our galaxy, where you have the mix of all these stellar populations, and where, for example, you're seeing in the simulation what we call the nuclear disk being formed, and this is what a simulation gives. There is a lot of complexity because there's a lot of factors that would change the simulation, so feedback from stars that die, and so on and so forth. Does this has anything to do with reality? That you could ask. Now, this is an exercise. Recently, you have these beautiful pictures. These are observations in other spirals made recently by James Webb Telescope. Here is showing 19 nearby face-on galaxies. So like I was showing you, the face-on, like if you see from above the galaxy. And you see that many of them have this structure we are seeing. Why is JWST able to do such a beautiful image? It has high-resolution image in the near-infrared, so you are able to peer the dust. Because what I didn't say yet is that in this disk there are stars, but there's a lot of dust. And the dust don't let you see the light of the stars. unless you are in a wavelength range that is like the infrared. Then you can peer into this dust and see this inner part. Of course, for an outer galaxy, it's easier because you're seeing it from above, from outside. From us, it's difficult because we are inside this disk wanting to see the bulge, right? So it's very complementary, the kind of information that will come from our galaxy and from external galaxies. Here, I would like to zoom to this specific galaxy, which may be similar to ours, where you have a nuclear ring that develops. You have also regions devoid of gas in the inner parts of the galaxy because the gas was kind of take out from these regions. And then also you have blobs that forms, and in these blobs of gas, we think you can also have extra star formation. Stars can form. So this whole process is very important. The two simulations I show you, and this data show that, well, there is some reality in what we are simulating. They are still simplified because they assume the galaxy is in isolation. But our galaxy is not isolated. And here I'm showing you a simulation of what we call a cosmological hydrodynamical simulation. So a simulation of gas and stars and dark matter that you're not seeing. And here you are seeing the galaxy again, face on and edge on. In the upper two plots, these are the stars, and low you are seeing, in the bottom, you're seeing the gas. What you see is that once in a while you have some balls that kind of cross here, and these are because the galaxy is not isolated, you see, and we get accretion. We accrete, our galaxy eats other galaxies nearby. This galaxy fell in our galaxy, and these stars could mix with the stars that are in our galaxy. So if you want to tell the story of our galaxy by understanding the stars that we have here, we should think that some of these stars were not formed here, were formed in another galaxy as well. That's very important because it's also a very nice gift of the nature, because if we figure out which are the stars that were accreted to our galaxy, we can then tell, even with a lot of detail, the history of another galaxy, which otherwise you would not manage because you would not have a telescope very strong or with a huge view to be able to get the details of stars in other galaxies, but you can do this for our galaxy. That was a simulation to show you that actually the galaxies are not isolated, but there is here the other kind of simulation, which is the high-resolution environmental simulation. It's called the Hestia simulation, which tries to simulate a volume that is similar to the one we live, because our galaxy, we know we are near, we are far, but in this big volume, we have a neighbor, is Andromeda. And so would this particular environment give even more details about the history of our galaxy? So this is what these simulations are trying to do. They are very high resolution. Here you are seeing a volume which contains two large spirals and also contain other galaxies, like we know for our galaxy. Our galaxy has satellite galaxies. Andromeda also has satellite galaxies. You can even look to them, and they were in the first picture I show you, Gaia, the Magellanic Clouds. If you go to the southern part, you see them very clearly in the sky when you go look. And we know we have also discovered a galaxy that was accreted to our galaxy, which is the Sagittarius dwarf galaxy. So we still see the Sagittarius. So this is all very important to put the main point here to tell you we don't live in isolation. So just like humans, we cannot live isolated, galaxies also do not live isolated. Just like humans, we are not living a life completely independent of all the things that are surrounding us. Same thing is the galaxy. And the galaxy is also aging. This is why we can do a field, we call the field that I work, which is Galactic Archaeology. What do you do in archaeology? You're going to look for past information that were there, the fossils that keep an information so that you can tell a story. So that's essentially the idea. And you saw that there is a huge complexity in this history of the formation of galaxies. There are a lot of internal processes playing, so bar formation, gas going here and there, accreted stars from other galaxies, and so on and so forth. And therefore, you have a lot of also difficulties to model that, because it's a very complex problem with a huge dimension, very large dimensions, and you need to also model very small dimensions. That's one of the big difficulties. So the Milky Way can then be used to provide extremely useful constraints to these simulations and to our view of how galaxies formed, even though we are at one galaxy. But what is the main point of this galaxy? We are inside the galaxy, so for our galaxy we see individual stars, and we will use individual stars as the fossil records that can tell us the history of our galaxy. When you look to an external galaxy, you see, because they are too far, you don't see the individual stars. You see integrated view of the whole thing. So you cannot date individual stars, only for very little more nearby galaxies with huge telescopes. So the stars are going to be used as fossil records from now on for what I will tell you. And let's go back to the map of Gaia then. Here you see again the disk of our galaxy. We are sitting inside the disk, so this is the view of the disk. When I look into the direction of the bulge, I see lots of stars. When I look above from the disk, I see less stars. I see the halo. And I see, for example, the Magellanic Clouds that you can see here in the south, right here. And there are other information in this data. But this is not the three-dimensional map that I want. This is how I see the galaxy on the sky. And I need to transform this information to construct this map so that we don't need to look our galaxy anymore only in a cartoon. So how do we do that? To map the galaxy and then to use these fossil records, I will need the precise distance, I will need to complement what Gaia is giving me, which is the positions of the stars, with more information, like we say, photometry, spectroscopy. And from that, I'm going to get all the three velocities of the stars. So because Gaia gives me the transverse velocity, I need the radial velocity as well. And I also get chemical elements. So I will build a map that's not only a position map, it's a multidimensional map full of information. And if I have a spectroscopy, I can even add to this map chemical information. The galaxy has stars of different composition, and the different composition of the stars are telling me a history, and that's what I'm going to use to tell the history of the galaxy. And one thing that is very nice, as I just told you before, a star that's accreted from another galaxy in our galaxy that I can now study in detail tells me about the story about that galaxy with detailed information, even chemical information. A star that was in the bulge part of the galaxy, very inner part of the galaxy, and is kicked out from that region, because this is also happening. You saw the bar was doing like this when it was like oscillated. Essentially, it's the stars that are going out, and you have something process that we call radio migration. Stars leave their birthplace and appear in another place. So this is, in one sense, complicating our job, but in another sense, it's a very nice news, because I can have a very nice information about the star that was there next to the center of the galaxy, now turns out to be here, and I can do a total detailed study of that star and understand a lot of what's going on in the inner part of the galaxy. Okay, so Gaia, the goal of Gaia was this. There you have a cartoon again of our galaxy in the background, and overplotted what the Gaia map is expected to be at the end of the Gaia mission. That's the region we would cover. That's amazing, because before that, most of our information was restricted in a volume smaller than this blue dot that you see in this figure. In this figure, we are sitting here, and essentially here is where most of the data of high quality will be. And then you see that the data of Gaia will even expected for end of mission to cover the bar area. What could we do is that once Gaia came out, this was, again, you're seeing the galaxy now, again, from above, always from above. The sun is here. Here should be the bar. And if you use only the Gaia data, which gives you the parallax, and you invert the parallax, you get the distance, but that is valid only for a very small volume. As soon as the parallax gets very small, and you cannot tell anymore the distance very well from stars that are too far away, you need extra information. Gaia is doing an amazing thing. Gaia, to measure parallax or an angle, Gaia has a precision that it can measure an angle, the angle that makes a 1 euro coin. If this 1 euro was sitting in the moon, put in the moon, Gaia would still measure that angle. But even like this, the stars are so far away and the volumes are so huge that this parallax is not enough to bring me to see everything unless I have complementary information. So here you are not seeing the bar, because this is using only the Gaia information. Now, we have developed a group where a team, what we call Star Horse team, where we combine the information of Gaia with more information. Which information? Photometry, more bands or colors of stars. And when we do that and treat this data in a very complex way, we can then obtain from that same data a different map. And what are you seeing now in this map? You're seeing a bar. And this we obtained not in the end of the Gaia. We managed to obtain that already at Gaia Data Release 2, which happened in 2018. And we create this map here now. This is before I show you what Gaia expect to get in the end of mission, which will be many years from now. And this is what we are already getting if we use Star Horse and complementary information, then Gaia complementary information. Here you have starting to make this map. For more, here I'm plotting more than 200 million stars. And we also made a movie of this, because there you are seeing face on. Look at this movie showing you are seeing the galaxy face on. And now you start overplotting the image that I show you, that for which we computed the distance of these stars. But now we are trying to see it edge on, and you're going to see that actually, you see there is a hole there, the bar. You cannot see the whole thing. There is a hole where Gaia cannot peer the dust. Gaia is in the optic, cannot peer the dust to see that inner part. And so this is where we were in 2019. And that's a comparison between what Gaia was expecting to get in the end of mission, what we already have with Star Wars. In Gaia DR3, when Gaia made a next release in EDR3, which was in the end of 2020, December, then the parallax were even better, because Gaia needs time. The parallax will get better the longer it's observed, because it's a repetition of observations, and that will give you much better results and proper motions, which is the stars moving on the sky. So we then had to assess our maps once this new data came out, and indeed we get even better maps with more details, here now containing almost more than 300 million stars, for which our distance were good. There is the sun, there you see the bar, and this is what our map when you would see the galaxy edge on. And this again, you see here is where the bulge of the galaxy is, the inner part of the galaxy, and the hole that you saw in the movie. So Gaia cannot peer into this dust, so you're not getting the information of the innermost part of the galaxy, which JWST was getting because it was looking from outside. Okay, so, but for that, we are discussing a project that's called Gaia Near-Infrared, which will be the next Gaia. Is a Gaia that can be seen in infrared, and hopefully this will turn reality in the future for the young people to study better the bulge with Gaia. Now, if I take the distance I show you with Gaia DR3, and now I again do that plot, but now here I'm zooming out, okay? Before I was showing you a box of 10 kiloparsecs in each side, and now I'm zooming to a 40 kiloparsec. And when I am in 40 kiloparsec box, I'm already seeing here was our sun, here was the bar, here is Sagittarius, the Sagittarius galaxy that's behind the bar, and here are the Magellanic Clouds. It's amazing because we are able to see, and this is the same thing, but now edge on. That's what it means. Z is the height from the midplane. So we are able to see this thing now. This is amazing. It's like we are traveling to outside our galaxy and look our galaxy. Of course, the map is still not complete, but we are getting there. Now, as I said, to expand this amazing legacy of Gaia, we have to combine it with spectroscopy. It's a much more expensive thing to do spectroscopy of stars. For that, because the stars of Gaia, they are almost 2 billion stars that Gaia have measured. And we cannot take spectra of 2 billion stars, not even of the 400 million I'm plotting for you here, I'm showing you here in these maps. We have to choose the best stars to do spectroscopy, or to use the spectroscopic surveys, as we call, that were around to try to understand if combining with Gaia we get more information. So this is a work that goes in parallel in this way. And this is, large missions are being starting, like WEAVE in the north, and for most that is coming from here, from the Institute and all its partners, where we are going to use multi-object spectroscopy. So we are going to, in one shot, get more than 1,600 spectra to be able to add the information of radio velocities and chemistry to these maps, which is important. Right? The star that's more close to us is the sun. This is an image of the sun, by the way, very beautiful, taken by Solar Orbit in March 2022. And it's a very high resolution image. It's beautiful to go online to see because you can zoom in the image, and this is our sun. What is interesting is that our sun was born, and we know very precisely it was born 4.6 billion years ago. And why do we care about this now? Well, because the composition of the gas that formed the sun at that time is still in the sun. So the chemistry that is today in the photosphere of the sun tells me what was the chemistry that was in the gas from which the sun formed 4.6 billion years ago. Now, just make the jump. If we know this, then if I take an older star, I know the gas properties 10 billion years ago if I find a star that's 10 billion years ago. And what if I found a star that's 13 billion years ago? I will understand the chemical composition of the gas 13 billion years ago. And that's possible only for the Milky Way, essentially, to that level of detail. This is the very important thing. The composition of the gas in the photosphere of a star is essentially preserved, is an information preserved, is a fossil record of what was going on in this galaxy at that time of formation of the star. So you need to know the age of the star, which is very complicated. For the case of the sun, it's easy because it's very close to us. So what is in the photosphere of the sun? Well, the composition is shown here. Most is hydrogen, helium, and then all the other chemical elements are essentially less than 1.5%. How is this 1.5% broken in different chemical elements? Here is more or less how this is broken. A lot of oxygen, a lot of carbon, a lot of nitrogen. And what is similar to this composition? Our bodies. So we are part of this universe, and we are made of these rests of stars as well. That's why we say we are the dust of the universe. We are part of this universe. We have a similar composition, okay? So now that's what I said. If I take all the stars than the sun, it's like I'm opening a window to the past. And this is why I'm doing galactic archaeology. Now, when the sun will die, it will become a planetary nebula, showing here also, this is a beautiful recent image by JWST for one typical planetary nebula, which is the dead of our sun. It will eject its outer layers and will live inside the central star that will become a white dwarf after. And this is one example of this. This will eject what? Will eject all these chemical elements that was in this photosphere, so the chemical that was already there, plus the chemical elements that the sun will make himself. Sun also makes elements. Yes, it makes. It makes essentially carbon, for example, carbon and nitrogen. So, but what about the other elements? It cannot make oxygen, cannot make other elements. For that, I need supernova stars. Here is a very beautiful image from MERCAT. It's a radio image of a supernova remnant. A star that has exploded a supernova and left a remnant. That's the shell we see. It's very rare because this is very roundish. We are usually to see other images where the supernova remnant is already very much dispersed. This is a beautiful image. And this is, for doing this, for becoming a supernova, you need more than the mass of our star, of the sun. You need to at least be 8 times the mass of the sun, and then you can then produce other chemical elements that the sun cannot produce, like, for example, oxygen. If a star like our sun is next to a white dwarf, which is the dead of another star like our sun, and this star is evolving like our sun and throws matter into this white dwarf, this will lead to a different kind of explosion that we call type 1a supernova, and this will make more iron. And there you go, the universe is very diverse and very intelligent. Now, let's say, when you had the supernova, you were left with a neutron star in the center or a black hole. Now, if they were in a binary system together, turning around one in another, and you can have a situation where 2 then neutron stars will merge, and that we have measured recently, and that will again produce other elements in the universe that neither the supernova alone could produce, not stars like our sun or not stars massive could produce by itself. And that's what built our periodic table. You can look to the periodic table like in this figure, where each element is colored by following where it's produced. So some elements are produced at the Big Bang, essentially hydrogen and helium, and then you have stars dying like it's reaching low masses like our sun, or you have this kind of binary system that I told you that give also the explosion of type 1a supernova, or the dying massive stars. So these kinds of stars and deads of stars are giving us chemical enrichment of our interstellar medium, chemical enrichment of our galaxy along its history. The galaxy is becoming more and more rich in chemical elements. And it's not only ours, it's whatever galaxy that has stars, because the stars form and die, form and die. These stars have some properties that we can organize them in luminosity, temperature, for example, and this is where the stars sit. They sit in a mean sequence here that we call mean sequence, where they are burning their hydrogen before they go off of the main sequence to become a red giant and then die. So the good thing is that our sun is here and has a very long lifetime of 10 billion years. And it has been sitting there for 4.6 billion years, but will be sitting there still for another long time before it then starts becoming a red giant. Its luminosity will increase, its temperature will go down, and it will become a giant. And by that time, it's so big that our Earth will be inside. But the good thing is that there is a long time to happen that. If our sun was a very massive star, it would have lived much less. And so that's why it's very good that we are next to the sun. Now, these stars here where I'm putting these are the stars that have long lifetimes. Why do I need to study and focus on the stars that have long lifetimes? Because those are the ones that I can use to trace the whole history of the galaxy. I will have stars that are older. If they are formed now, they would live longer than 13 billion years, depending on their mass, if they have very small mass. So those are the stars, and we call them the FGK stars. These are the stars that we are using in the surveys and go for them mostly. We are also checking the other stars, but to do galactic archaeology, this is one of the main. So we will focus on these long-lived stars, and then you can answer many questions that I don't have the time to go here. But for example, you having stars that live the whole life of the galaxy, we can translate this sky view in real positions in these maps, and then from there we can use this information, chemistry, and their velocities to trace their past merger events, to see which stars was here, which star came here, which star was formed near the sun, which star came from the bulge. This is all what we call stellar populations. And we can use also the detailed chemistry to trace the history. For example, in the thick disk, we see there is a chemical pattern that is what you get if you are forming in very early phases, where not all the other contributors to the chemistry can already play a role. So this is what we use for the stars. We can we can figure out that our disk was formed actually inside out. We can observe this radial migration happening, stars that were forming the inner galaxy that are now here. We can see this disk flaring also in other stars, not only in the Cepheids. We can compare the Milky Way with galaxies at high redshift. What it means, high redshift? That I go and observe farther and farther galaxies. So I'm going towards the past because the light has a finite speed. So is what JWST is also doing. Look to very high redshift galaxies. So galaxies that are formed just after the Big Bang. So this is one way. The other way is to look here in our backyard, the oldest stars of the Milky Way. So that's what we are going to do, and we can compare. Are we seeing things that are related, or are we seeing things that are not at all related? So that's also a very nice field of work right now. And we can compare the present Milky Way with other local volume galaxies, as I showed you before, Andromeda, or also these other ones, beautiful spirals. And we can also constrain the nucleosynthetic size, where the different chemical elements are made, and also add more constraints about when I have very old stars and very metal-poor stars that still had essentially no metals, no iron, no anything, because they were just starting the evolution, the oldest ones. Then I can also understand how were the first stars enriching the universe. Were the same? Were these supernova that I told you the same that we have today? Because we still have supernova exploding today. Were they the same just a couple of million years after the Big Bang? So these questions is amazing that we can answer just from the Big Bang, and there's a lot of questions, okay? Let's go back to the map then. You know that now, after I explained to you, you know that in this map here that we were discussing with Gaia plus colors of stars, and where we found the bar, each point here is a star, and each star has all what I explained to you, just like the sun. Chemistry that's preserved, and a lot of information, which is this chemistry, how this chemistry was obtained along the time, right? And here you are seeing again the upper view, but you are seeing now the coverage of our galaxy now, for which we have spectroscopy. And you see that this here, I put it, there is an ellipse here. This is where the bar is. And you see that essentially one survey is covering very much that region. The others not so much. And why? Because this is apogee. And apogee is again in the near infrared and could peer the dust and see the inner parts of the galaxy. So that was again a revolution. Not only Gaia, but Gaia combined with apogee is a revolution because we are opening a view to a place of our galaxy that you saw that we only with Gaia we wouldn't reach, which is the hole here. So we are filling in this hole by going to apogee. And of course, for these samples of spectroscopy, you can get precise distance because you have more information and also chemistry. One of the things that we get, for example, are, which was amazing with respect to apogee, was, for example, this map. I'm again looking the galaxy from above, but now I'm looking to the before we are looking to a box of 10 kiloparsecs, now we are looking to a box of 4 kiloparsec. We are really there in the center. And we are looking to how the velocities behave in that region. And you see that there is a pattern. And that pattern is like that. So some are blue shifted, the other are red shifted. The stars are going against the direction that of the observer, and the others coming towards the direction of the observer, and it gives you this pattern. And what does it mean? This means that this is what will happen if you have a bar in the center of the galaxy. But for the first time, you can really see this in velocity space, which is beautiful. You can see this from both sides. That's what's important, from the both sides of the distribution, right? Which is minus mean below, beyond the bar, you see? So we are here, the bar, and we can see even beyond. And this is what expects for example, for some simulations of the simulations I showed you in the beginning. Some of them have bar, and they look to the velocity profile of this, and they find similar things. We can do more. I'm not going to really come here in complication, but this is essentially, I take the stars that I got. So this, for example, in this case, 8,000. The problem is this. I start with a box for which I have Gaia and photometry information or color information for 30 million in that green box I had shown before. Then for the stars for which I have spectroscopy in the inner part of the galaxy with apogee is like 30,000. And by the time I really took out the contamination of the disk and want to be really inside, I am working with samples of thousands only. So that's the difficulty. But for this sample of thousands, I can get orbits. And I can then start studying what we call chemodynamical diagrams. Diagrams that give information of the orbits of the stars together with its chemistry. And for example, if I see here, for example, I'm just showing how the Zmax, so the star has an orbit, how far the stars are going from the midplane, and how eccentric is this orbit. And this, I throw my stars here, colored by how much metals they have, and I see that I have a lot of stars very metal rich, but they are more into the plane of the galaxy. They don't, I'm talking about the very inner parts of the galaxy. They don't go beyond too much. But when I go far from the midplane, I get more and more metal poor stars, stars that have not been enriched so much. So this is telling me about the history of the formation of the stars in the inner part of the galaxy. And then we discuss in this work that it was possible to see that in the inner galaxy we have inner thick disk. A piece of the thick disk is also in this sample, thin disk, but also an old spheroidal bulge in the middle and the bar, right? And we find a reservoir. That's what I would like to call your attention. A reservoir of stars that are very much more metal-rich than the sun. So the quantity of chemical elements in the sun is essentially there. You have a lot of stars that are at least twice the composition of the sun in terms of the amount of metals. That's very interesting. As I said, the stars migrate. They come from the inner galaxy. So I am here in the galactic center. For example, here's the galactic center. We are sitting here. Z is how high we are from the midplane, as I said, and R is the radius between the galactic center and here, and we are sitting here. And if we look to the stars that are sitting here now, we know from simulations, we think from simulations that actually they are sitting here, but they came from burst radius that are much more all over the galaxy. And if I look to the simulation, I can, but to the real stars I cannot, I can see that a lot of stars came from the region 0 to 5, which was here, but they are now here. And so on. I can put this cylinder in different places of the galaxy, and I always want to see that stars from the inner galaxy are coming here, are coming to other volumes. This is what we call radial migration. But this is a simulation. Is there any truth on that? So now we can do this kind of thing. We can go to 1 kiloparsec volume, look to a very good age, in this case not Gaia, but this is asteroseismology, another method to measure ages, and we can plot, okay, I will plot here the number of stars, the fraction of stars with a different chemical composition, and I have their ages. So if I told you that the evolution of the metallists was increasing with time because you need the star to die, contribute another form, die, contribute, so the amount of metals is increasing with time. How could it be that when we plotted this with age, we find that the youngest stars should be the most metal rich, the ones that have more metals, but we find instead that the most metal riches in this tail of this distribution are old. So they cannot be formed here. They are essentially showing me this plot is the galaxy saying, hey, these stars are not formed here. They came from the inner galaxy. Have a look. Have a look in the other properties of these stars. So that's a nice thing we can do. Where did these stars came from? Well, I just showed you before that these stars could came from the region we are analyzing before, which has a lot of stars that are twice the metallicity of the sun. So another thing interesting you can do with other samples, you can also you can use different surveys and then obtain age for a small volume that nearby us, and we can find, for example, the properties of the thick disk. I find the thick disk to be very old, above 11 giga-years old, and is all made at once, very coeval. It's not like it goes from 7 to 11. No, it's a very clear distribution of age. So it was like, was made, right? And but I don't believe this data. Then go and do the same with other surveys. And we have this now moment where we can check our information several ways. And they are giving very similar information. This is very beautiful. Okay, now there are other data we can use, and it's again Gaia, which is amazing, is to look for these supermetal-rich stars, for example. I'm finishing almost, but then the supermetal-rich stars, they give me, they almost like they came with a flag. Hey, I'm not from here, I am a migrator. The others, it's hard to figure them out. You need to do more of a job. But if they are more than twice the metallicity of the sun, that is not much. They have to come from somewhere else. And that's what they are doing. So let's study these stars. How could they came here? What was the main thing causing them to come here? So in recent papers, we could then use an amazing other sample. So Gaia, as I told you, measure the positions, the velocity, translational velocity, but need the complementarity. And I was discussing several surveys. But Gaia itself provides a survey, which is called the RVS. Is some spectra, and from this spectra you can also get information. It's not covering the whole galaxy, is in a smaller volume, and this is what I'm showing here. It's covering this volume here. So here is the sun, 8, and it's covering a volume of around 1 kiloparsec too. And but these stars are exquisite because Gaia see the whole thing, not on the low and the southern and northern hemisphere. He see the whole thing. It's not in the Earth. It's orbiting the Earth, and has fantastic spectra because the spectra are not disturbed by the atmosphere of the Earth, which is another problem we have if we take spectra from here. So these data are exquisite. And when combining this with more information that came in Gaia DR3, which is another kind of information which we call XP spectra, to be more technical, then using a machine learning way to get information, we extract very good stellar parameters from these samples of stars. And we can get a fantastic sample of over 170,000 stars within this 1 kiloparsec around us that has the difference that have exquisite parallax, very good radio velocities, metallicities, and other information. And what is this thing showing us? It shows us that actually the most massive stars, here I'm just showing you, if I take in these stars the most metal-rich ones and plot here, the most that has most of metallicity, along the age and their ages, I see that at some point, here shown in this yellow thing, this metal-rich stars stopping coming here. Why? That's what this plot is telling me. At some point, 3 giga-years ago, more or less, these metal-rich stars are not coming here anymore. Why is that? Do they need more time to come here? Or the thing that was sending them here stop, right? So we here interpret that the thing that was sending here was the bar, and essentially the bar was buckling around this time, right? And so have a punch of stars and then stop. And if that is happening, this could cause also to shake the gas in the galaxy, essentially, and could create a star formation episode, forming a lot of stars by that time. And if we now plot here for this sample, the metallicity versus the age, we see the distribution of all these stars, and we see suddenly there is a bunch of stars here, which correspond more or less to the same time where the stars more metal-rich didn't come. I know this is complex, but just to give a flavor of the kind of discussions we can get. And this is very beautiful. So this is the final one, using again this sample. Now, essentially, this is the distribution radius from the galactic center. The galactic center here has a hole, because as I said, Gaia cannot see the center. And here, if we analyze the stars that are nearby to us, those that are showing here in a red contour, so around 1 kilometer, we have very good age for those stars. And what we find? We find very old stars, older than 12 billion years, just here nearby. And interesting, they are not in halo orbits, they are just like the sun around the disk. This was not expected, because you would expect those to be a bit younger. And we are seeing very, very old disk formed, right? This is very interesting, because also from the high redshift observations with ALMA and JWST, they are detecting cold disks already formed very early on, very after the Big Bang. Soon after the Big Bang. And the properties of these disks and the properties of the stars that we are finding here, they are tracing also on a very old disk, are very similar in some sense. So this is also very interesting. And what I want to say is that with this data, with Gaia, with spectroscopy, with all this information we have, we are really, it's just to sit, look to the data in a good way to discover more things. And there's a plethora of topics you can work. It's a very amazing moment. But of course, it's not ideal, because as I show you, the coverage with spectroscopy, which gives you all this extra information of chemistry, is minor in the southern hemisphere. Here I'm showing you again the galaxy from above with the spectroscopic surveys, and you see here most of the disk, outer disk is covered, of course, in the north hemisphere, but from the southern hemisphere we have some surveys as well. But only apogee was reaching the bar, and we have a lack of data here. And this is what we are going to complement with foremost, with this telescope that will do multi-object spectroscopy. And we are, specifically myself and Ivan Minshev are the PIs of this survey, which will survey the stars in the southern hemisphere and give us many more constraints of this inner part of the galaxy and bulge, which is where a lot of action is taking place in the galaxy. So that's what we are going to do, using the VISTA telescope that is an ESO telescope and is in Chile. Here's a beautiful picture of this telescope with the Milky Way that you can see beautifully if you are there. And these are some properties of characteristics of the instrument that will be put inside that telescope, which is the foremost. And you see here, there's 2,400 fibers. So we will be doing this. Of course, nobody does the work alone. So this is a group. There's a lot of people. More information are in this messenger publication of ESO. And I will finalize with this just now, last week, 29th of February. The first piece of the instrument that's been constructed here since many years was sent to ESO and left IPA. And we hope it's traveling well towards Chile. And, well, that is it. So we are in a great moment to do galactic archaeology. We call it the gold age of galactic archaeology. But in some sense, we are in a gold moment for doing astrophysics. Because as you saw the pictures I show you of the sun, of high redshift, of nearby galaxies, of our Milky Way, I mean, it's really, really a very amazing time to be doing this research. So I hope you will join us in this beauty. Thank you.